oceanography, climate, and intelligence. He worked for Martin Marietta in Denver on various space projects, and that's where Ed, John, and I met. He also worked for MITRE, Ball Aerospace, and Boeing, where he was a technical fellow. He was adjunct faculty at the University of Colorado with one successful PhD student, and in retirement was a proposal reviewer for NASA space science programs. Ed has advised the National Academy of Sciences and NASA on planning technology programs related to astrophysics. Ed and John have co-authored 4 books on electro-optics, and Ed was the conference chair and editor of the Proceedings of a Conference on Orbital Dynamics. He's author or co-author of 79 professional journal articles and related publications. He's a reviewer for the Journal of Optical Engineering. Ed is retired, but is currently teaching cosmology to adult students, coaching elite high school students, and giving talks like this one. I met Ed when I was fresh out of undergrad, and he welcomed me as a 21-year-old, blonde, energetic young lady talking 100 miles an hour about subatomic physics with a very strong Southern accent. I appreciated that he took me at face value, though I did catch him sort of shaking his head from time to time, perhaps to embrace the incongruity of it all. One of the things I appreciate about Ed's influence in my early career was a time when our group of lunchmates, me and Ed and several PhD nuclear physicists from Lawrence Livermore, walked to the grocery store for lunch. I remember Ed had a red bell pepper for lunch that day. I was really upset that day by something that my then boss had said to me, and I started to cry. And he asked, "Do you know why you're crying?" And I said, "Yes, I am absolutely furious." And he said, "Well, good. I just wanted to be sure you knew." So something about his support in that non-patronizing way during that specific interchange established in me a long-standing value and goal to embrace the fullness of who I am in my vocation. That's a vocation that markedly prefers the left to the right side of the brain. And I will say after 35, 40 years in this business, that I think that we all benefit from bringing the very fullness of who we are to our vocations. So thank you to Ed for that. Now, John Lester Miller has a BS in physics from the wrong USC, the University of Southern California, MS from Cal State, and an MBA in Management of Technology from Regis University here in Denver. The three of us have deep Denver roots. He's worked on several classified space telescopes and space instrumentation. He has advised the UN, National Academy of Science, financial institutions, and others on infrared technology. John worked at Griffith Observatory, Mount Wilson, and Palomar Observatory, where Edwin Hubble worked, Mauna Kea Observatory, Rockwell International on a space telescope, Lockheed Martin Denver, again, where all three of us met, and Martin Orlando. Then FLIR Systems as Chief Technical Officer, and he was fired in 2015. So he just simply cannot keep a job. But like Ed, he is retired, but consults. He's an SPIE fellow and wrote over 100 papers and 4 books with Ed. Miller is a chair of the planet's largest IR conference at SPIE and a past reviewer of the Journal of Optical Engineering. John and I met after Ed and I had each moved to different work areas. John was my boss at that time. And honestly, the stories that he and I could tell about our work together would really keep us all entertained for quite a while. There was an awful lot of creative energy in that 2-person cubicle. That cubicle was filled with those calendar sheets from the Word of the Day calendar. It was topped at the top of the cubicle. We had placed this 3-foot plastic duck, and John sports it in his home decor to this day. John, did you bring it to the meeting, this 3-foot plastic duck?
I did not, Laura.
Oh, I was hoping you would have it here as a demo. My favorite story about that period of my life is one that demonstrates the close relationships that we develop with our coworkers, you know, when you can anticipate their thoughts and their responses. On a business trip to Los Angeles one time, I was driving to dinner and John and an old friend of his was in the car. John told me to turn right and I turned left, and that was what John had meant. His friend dove for the door handle screaming, "Get me out of the car, I want out." But more seriously, I have degrees in math and physics. I've done research in high energy particle physics, theoretical nuclear physics, but really I learned what I needed to know to perform the majority of my very satisfying career from none other than John Lester Miller. Through one of the freaks of our aerospace business, I was given 2 weeks notice for a layoff. And in that 2 weeks, John sat down and taught me infrared sensor design, complete with assigned reading and homework. And that put me on the path of space sensor development, and I have never looked back. So you never know what a 2-week period is going to do for your life, whether you turn right or left. So everyone, please mute your mics. It is time to be entertained by their Hubble talk.
Thank you so much, Laura. Thank you. We're going to have a good time tonight. I'm going to ask you to hold questions to the end because we might be running a little long on this. First, we're going to have a few charts on introduction and why there are space telescopes. Then the history of the Hubble Telescope, the Hubble design and program, a couple of charts of just ooh-ah charts on the launch of the Hubble, and then Ed's going to talk about the primary mirror disaster and fixes. Then we have the other ooh-ah portion of this talk, which is about 30, 40 fantastic images and discoveries that we'll go through rather quick, and you can read some of this stuff on the video afterwards. And then a few page conclusion. So why space telescopes? There's a lot of them. Off is the Kobe telescope of several years ago. These are basically to get above the Earth's atmosphere. The atmosphere absorbs and scatters all wavelengths of light, period. It's a large absorber and scatter of ultraviolet, X-rays and such, and gamma rays, which is good for us humans, actually. It's a minor but real scatter of visible light. The sky is blue because it scatters blue light. And even green light is absorbed and scattered by our atmosphere. It's a minor scatter of infrared light, but it can be a major absorber depending on the wavelength, which is why we have climate change and global warming, because the atmosphere absorbs in the infrared at key wavelengths. The atmosphere also causes scintillation or twinkle, which is due to variations in the index of refraction or speed of light along the path length. There was an SDI technology synthetic guide star via phase conjugation that greatly mitigates this for ground telescopes. However, it's not perfect. Getting out of the atmosphere is perfect. Also, space telescopes avoid human cultural effects like light pollution, atmospheric pollution, aircrafts, and what's becoming a major issue is low Earth orbit orbiting satellites. With the proliferation of low Earth orbiting satellites and these billionaires wanting to launch thousands of satellites, it can really screw up observations. A very low light level observation could be 20 or 30 hours of exposures, and where they do 4 or 5 hours per night for 4 or 5 nights. And even though it's a narrow field of view, the chance of one of these low Earth orbiting new satellites flying through and ruining the data is getting quite high. There are many space telescopes. The Hubble's not the only one. The Spitzer infrared is one, the Planck. This was, I believe this is Owen Garriott, and he was servicing a space telescope on the Skylab back in the day. So the Hubble. So let me just start peeling the onion back a little bit, some little facts about the Hubble in this intro. It was designed to operate in the ultraviolet through the shortwave infrared. Now, ultraviolet, this is important. It's a shorter wavelength and requires the most accurately formed optics. And this is foreshadowing that a little bit. It's got a 2.4 meter primary mirror. It's in low Earth orbit at approximately 340 miles, which is the highest orbit ever achieved by the shuttle. It was servable by humans. It was made from the beginning for the shuttle to be able to grab it and service it. There's been others as well like that. Well, when we made this chart a month or two ago, we said, no, not anymore. But I'll show you, they put a docking port on the shuttle in 2009. And remember about 2 weeks ago, there was some tourist yahoos that went up. There was like 3 or 4 of them. They went up over 400 miles. And now there's chatter that they could, some of these commercial companies could actually dock with the docking port, put on the space telescope, and potentially do some minor service. It has been in service since 1990, and probably it could have 35 years of service. It's ending the near of its life due to gyroscope and pointing errors. One gyro is dead. There's some points in the sky it can't point to. So it is getting all into. And here's another image of the telescope being deployed. Some fun facts. It has made more than 1.3 million observations, traveled more than 4 billion miles, and has been used in over 15,000 scientific papers. There's not many single pieces of machinery that has spawned 15,000 scientific papers. A little history. First, who was Edwin Hubble? Well, he was an astronomer. For those of you in LA, he worked at Mount Wilson and Palomar. His office was in Pasadena. He worked at the 100-inch at the Angeles Crest and the 200-inch. But where he made most of his discoveries was in the 100-inch Hooker telescope. And that's yours truly when I worked there back many decades ago. He has astronomy degrees from Oxford and University of Chicago and excelled in every subject except spelling. So those of you that know me know we must be a kindred spirit. He proved that nebula were both other galaxies and gas structures within ours, and you'll see many in the ooh and ah section. That proved the universe is beyond the Milky Way, and that was a big deal back in those days because that was a big argument. He started classifying galaxies as we know them today, but the biggest thing he did was he determined the universe was expanding and even caused Einstein to pull his fudge factor out of his equations. Unfortunately, he did not get the Nobel Prize because they didn't give it separately for astronomy in those days, although he should have. He died in 1953 in Pasadena, and no one knows what his wife did with his remains. So the Hubble space telescopes have been discussed since the 20s. The first paper in it was by Spitzer of the Spitzer Infrared Telescope in 1940. However, who really pioneered it was Nancy Grace Roman, NASA's first chief astronomer. And she's often called the mother of Hubble. Here she is discussing the early Hubble model with Edwin Aldrin. Finally, NASA got on board in 1977, issued a contract to Lockheed Sunnyvale for $200 million for the development and manufacture. The launch costs were extra. Astronaut servicing was not part of it. That was extra, and so were the instruments. It was expected to launch in the early 80s, launched in 1990. It was plagued by technical, budget, and schedule problems. Estimates vary, but somewhere around $1.5 billion at its launch. The mirror, which Ed will talk about, was made by Perkin-Elmer, now Emergent, in Connecticut. And Kodak and iTech actually made backup mirrors. And here's a list of all the service missions and all the shuttle visits to the Hubble. I'm not going to read through this. I'll leave it for a few seconds. So if you watch the video, you can, and are interested, you can pause it and read it. This is some of the some of the amazing observations and amazing accomplishments it has done, courtesy of Lockheed Martin. Okay, the design and program. The prime requirements for this was a space telescope to be launched by the space shuttle into low Earth orbit. It was astronaut serviceable. And that was important for two reasons. One is it fixed it, as Ed will tell you about. And key to understand, unlike other telescopes launched, the Hubble had technology refreshment. We weren't stuck into the first technologies that were launched on it in 1990, which were probably technology cut off close to 10 years earlier, 1980 or 84. We could pull the instruments out and put new technology, better instruments in it. So the last service mission was in 2009, but that's got 20 years, over 20 years after the launch of new technology on it. It has more than 400,000 parts and 26,000 miles of wiring. It's about the size of a railroad car. And this is the docking port that was put in 2009 because the Hubble outlived the space shuttle. And the idea here was a future unmanned thing could dock with this and deorbit it. But some of these commercial companies are saying, you know, we could dock with that too. So we shall see. One of the things I want to talk about just briefly was its accuracy and pointing. Not only was it incredible in light gathering and detection and instrumentation, it could point to 7/1000th of an arc second, or about the width of a human hair seen at a distance of 1 mile, or to put a laser beam on President Roosevelt's head on a dime at 200 miles away. It was all solar powered. It all works off of solar power, and it has no thrusters. A brilliant idea is it doesn't have little retro rockets that fire. That would, number one, run out of fuel, and number two, spew out effluent and contamination. Instead, it uses reaction wheels or big fly wheels that can tilt and turn it, kind of like the fidget spinners that as you see today. When you try to turn it, it gives you some resistance. It uses that to point itself. So here's a cutaway of the spacecraft. It has solar cells. I'm getting an error saying there's no video recording, Bruce. But it has solar cells, panels, obviously antennas. Yeah. It has the telescope is here, and the light comes in here, hits the primary, goes up here, hits the secondary, and comes down through this nozzle here, which is a baffle, into the instruments. And there's axial and there's online instruments. And here's a more detailed blow up if you're interested about it. It's got lots of pieces, lots of baffles, and most or all the baffles were coated with something called Martin Black, which was developed in Martin, Denver when Ed and I and Laura worked there. It has hosted numerous instruments throughout the years. Again, it was amazing that we could service this, pull an instrument out and put a new technology one in. It's designed to hold 6 instruments. One is a fine guidance sensor, which helps it point so accurately, and that's not really a science instrument. One was CoStar, that we'll talk about. So it really had 4 up until the time CoStar was pulled out. So the telescope design was a Ritchie Cretan, and it has a hyperbolic primary and secondary. So the light comes in, hits the primary, goes to the secondary, and comes down to focus here. And then it gets bounced off to the instruments. This design is used a lot. The Keck has this, the Subaru, another ground-based telescope. It has excellent off-axis rejection for straight light, doesn't have straight light problems. It has advantages of wide field of view and eliminates off-axis aberrations such as coma, and important for a space telescope is a compact design. Now, an interesting little side note, the 100-inch hooker that I showed earlier and a 200-inch Hale was supposed to be this design. But Ritchie and Hale had a falling out. Hale thought it was too hard to test the exact high quality curvatures and decided to go with a different design. And there's the manufacturing of the mirror. It was made by PerkinElmer in Danbury, Connecticut. And there were backup mirrors made by Kodak and ITAC. There's an image of a guy making a mirror with no clean suit on or anything. Since this 2.4 meter mirror was to provide excellent images in the ultraviolet, not violet, it needs to be grounded in the best shape or figure. It was able to image 100 nanometer wavelength, which is very short. The shorter the wavelength, the more accurately it has to be designed. We believe never has a mirror this size been ground so accurate. If the Hubble was scaled up to equal the width of the North American continent, the highest hill or lowest valley would be a mere few inches from its surface. The entire telescope took 7 years and 4 million man-hours to make. On-axis reflective telescopes have a lot of benefits like no chromatic aberration and such, but they have some drawbacks. If I go back to this secondary mirror blocks some of the light coming in. And more importantly, it also has to be supported by a metering structure. And on the Hubble, it was spokes. It was 4 spokes, right and left. And you'll see that in its images with bright stars. You'll see 4 spokes coming off them. And that's scattered light from the support structure of the secondary. Now, in all fairness, the Hubble wasn't made to image bright stars. It was made to image this kind of stuff. The dim nebulas, dim galaxies, and broad non-point source images like Jupiter and Saturn, which you'll see some amazing images of those. The design had to pioneer getting an astronomical telescope into orbit, pointing it, being serviceable by the shuttle, and supposed to be deorbited by the shuttle, but it actually outlived the shuttle. Now the launch of the shuttle. So it was launched. So it was successfully launched. Here's an image of how it was deployed using the arm, and here's the actual deployment of it. So it was successfully launched, put into orbit, and here's an image of it in orbit. Another beautiful image. And now first light, which is what astronomers call when they get the first image on a camera or telescope. And with that, let me turn it over to Ed, and I'll stop sharing now. Ed?
Ed is here, and I'm going to share my screen. Yell if you don't see it, and I'm going into presentation mode. Laura was having a little fun with John earlier about having a picture in the infrared. There's me in the infrared. So let's talk about what we all of us who were following space telescopes in the early 90s were astonished to discover that the first images were far less than desirable. These are pictures from what is called the Wide Field Planetary Camera. I'm going to talk about this quite a bit, abbreviated this way. And the expectation originally was we would see individual stars in these kinds of images. And here's a blow up of this region, and it's just a fuzzy mess. And the reason was that the optics were defective. Principally, and almost entirely, the primary mirror that John talked about was defective. Many of us are familiar with this issue now. The mirror is just a spectacularly good product, except it has spherical aberration. And so most of what I'm going to talk about is how that problem got solved. The principal way it got solved, which I'll get to a little bit later, is the installation of corrective optics called CoStar. I'm not going to talk about that too much right now. But the goal was to figure out, first of all, why aren't we seeing individual stars or small clusters of stars? And why are the images so dim? I mean, the technical public knows that there was a problem with the image resolution, but the real problem for the astronomers was the images were very dim, and I'll show you why that happened. This is the kind of picture we intended to get of this cluster. This is an image taken from the current wide field planetary camera, and I'll explain the history of that. So first thing we have to do is talk about what limits the performance of imaging systems, and it has to do with how light interacts with obscurations that it encounters. And the aperture of a telescope is such an obscuration. In a perfectly designed system, we expect to get a point object, an object so far away, like an unresolved star. We expect it to produce what is called an Airy Disk. It looks like this, and I've blown the Airy Disk up so you can see that not only is there a central peak, but there is a series of rings, and we want this peak in the center to be very tall compared to these rings. Now I'll show you in a second. This is what the actual performance was. The first ring here has a lot of energy in it. This is a specification for how Hubble was supposed to perform. And don't be confused by this. This is imagery from a book about the problem with the telescope. These are not to scale. I'm going to show you the scale in 1 second. This is how big this peak was. And this explains why the images and the spectroscopy that was done early in the days of Hubble in 1990 was such a disappointment, because the brightest objects did not have a peak up here. They had a peak way down here, about 1/6 of the specified value. Now, I'll tell you later how this was all diagnosed, but the function of the primary telescope, the primary mirror, secondary mirror, and other optics, is to convey near perfect beams of light to cameras and spectrometers and other instruments. And that means everything has to work correctly. All the optics have to be the right shape, they have to be in the right place, they have to have the right tilt with respect to the propagation of the light. And the way opticians deal with this is they worry about the phase of the light that's being conveyed. And let me illustrate here in a second. This is what we want. We want a phase front coming to instruments that is uniform. These illustrate various kinds of defects that can occur. Hubble has a whole bunch of this. And you can look this up. There's a link here when you get the notes. This is a live link, and you can go to the appropriate article in Wikipedia to learn more about this. Now, all of us have been to the eye doctor. Some of us have to have eye correction. And some of the terms you'll see here, this is an optician's layout of the different kinds of defects I just showed you. You'll recognize some of these terms. Like most of us, particularly people our age, have astigmatism. We have coma. An advanced diagnosis of your eye might reveal something called trefoil, and there are various kinds of trefoil. There's quadrifoil and so forth. So ophthalmologists are introduced to this classification scheme, and they want this for all of us. They want this kind of light leaving your lens on the way to your retina. And here's some illustration of a tilted phase front. Means the objects in the image are misplaced there, because it's as if you tilt your head when you're looking in the mirror. Everything appears to move. Here's astigmatism, which is something I have, and if I look at a distant street light without my glasses, I see multiple street lights. I don't just see one bright spot. Here's a focus problem, and here's what Hubble has. Spherical aberration. And this is creates all sorts of problems for these scientific instruments receiving the beam of light. And here's the cartoon illustrating this. A lens that produces focus without any aberration. All the rays, independent of where they strike the optics, they all focus at the same point. Spherical aberration has this property, that the perimeter rays focus closer and the central rays focus farther out. So you get what's called a circle of confusion, because there's a sense of focus all the way from this point here over to this point here. Now there's one number the opticians at Perkin-Elmer worried about. It's called the conic constant, and they kept measuring it when they were producing the Hubble mirror. The design specified that they worked to this number for the conic constant. Later it was determined they actually produced this. Seems like a small difference, and it is. I'll show you in a second right here. Here's the design, this dashed line. This is as manufactured, the dashed line, as manufactured. Here's the hyperbola, and this is a section of a hyperbola that John talked about. Here's the actual product they got. There's a 2 micron difference out at the edge of the mirror. Remember, the mirror is 2.4 meters in diameter. This is not something you could detect just looking at the mirror. You have to put it into an instrumentation that is very sensitive to this kind of thing. But we're dealing with millionths of a meter. And so the actual production object deviated, we now know, from the design by 2 microns. And part of the problem was the bulk of the problem was the test equipment that they used to determine the shape of the mirror that they had produced was inherited. Furthermore, no end-to-end testing was done of the entire telescope train. These days we don't do this, or we have adaptive optics where we can change the shape of the mirror dynamically once it gets into its environment. But for Hubble, they never tested from the primary mirror through the sequence of mirrors and lenses into the instruments. And here's a quote, you can read that at your leisure. But the summary is, no one tested the complete telescope before launch. And here's the test equipment layout. Light comes in, bounces around here, and we should have sensed this problem. In addition to inheriting this test equipment, there's a defect here that was discovered later in how the spacing of these 2 pieces, see, this is the primary mirror, this spacing to this field lens was incorrect because washers were put in upside down when they assembled the test equipment for this application. So there was a series of mistakes that would have been detected if the telescope was tested from end to end. Now, let's go back to the issue of the wide field planetary camera. This camera does not sit in the same spot as the instruments that were later corrected with the CoStar optics I mentioned. We'll go into this in more detail. This is the first type of picture they were able to get using the first generation wide field camera that was launched just as it was designed, expecting the primary mirror and secondary mirror to perform properly, and they didn't, and you get this result, which was a big disappointment. In 1993, astronauts installed an upgrade called WIFPIC 2 that made an improvement. It wasn't until, well, I have the dates on here, wasn't until 2009 that the current wide field camera was installed, and now we're getting this kind of detail where we can see small groups of stars in this galaxy. The CoStar instrumentation couldn't fix this because the beam path to the wide field camera is not within reach for where they could install the CoStar corrective optics. So in the next few minutes, I'm going to talk about what COSTAR did. The title of it includes the word axial. So you have to understand there are radial instruments, and the wide field camera is a radial instrument, and there are axial instruments. A COSTAR could only fix the axial instrument. So here's the same drawing John showed you. Here's the primary, secondary mirror, and imagine a disk of equipment here. These are the radial instruments, which include wide field camera and something called fine guidance sensors. The axial instruments are back here, and these could, the light coming to them could be fixed by installing corrective optics, and these are the current optics or instruments that reside in that space. So the genius behind fixing the axial instruments is this guy, Chris Burrows, who used mathematical techniques. If I have time, I'll show you what he did. He employed the fact that the Hubble Space Telescope has a movable secondary mirror. So we go back. This mirror can be moved back and forth along the axis of the telescope. And by doing that, he took a series of images and diagnosed those in a mathematical sense and determined what was wrong with the optical system and narrowed the problem down to a curvature problem in the primary mirror. Jim Crocker, who was at Johns Hopkins at the time and recently retired from Lockheed, Denver, he had this idea in mind that you could have mirrors that flip in, sort of like this European-style shower head. You could flip mirrors in that make corrections for the axial instruments. Mark Bodema at Ball Aerospace did much of the design work to figure out what the shape of these little mirrors had to be. And the mirrors I'm talking about are a little bit bigger than a quarter. And so he was the primary designer. Unfortunately, he died in 1992 before the COSTAR instrument could be installed, and that happened in 1993. But his very talented sidekick, Bob Woodruff, finalized the design, and we got correction. Now, COSTAR is a big success. I'll show you an example in a second, but it's very expensive because it required an astronaut flight on the shuttle, which was not cheap. But it demonstrated that humans could work around optics and fix them. It did not improve the performance of the wide field camera or the fine guidance sensors because those are radial instruments, not axial instruments. And they had to take out the high-speed photometer, one of the original instruments, to make room for the COSTAR optics. Camera field of view suffered on all instruments when they did this. And the faint object spectrograph, one of the original instruments, its performance was reduced. But I'm going to show you now the improvement we get. So originally, the optics did not meet the spec by a factor of 6. So that central core I talked about of energy that you should have seen from an individual star or a dim object, that was only 15% of what they were trying to get to, 80% performance. And here's the difference. Now this is the performance of an axial instrument, the faint object camera, and before COSTAR, this is the bundle of light that camera was fed by the optics. After COSTAR, we got this. Dramatic increase of, in fact, a factor of 6, and that essentially met the standard that Hubble originally had for the performance of the optics. Here's the layout of COSTAR. This is something like the size of a phone booth. It has all these arms that flip down like the Jim Crocker concept of they had to be packaged in one way, and then once they got installed in the telescope, these arms flipped down to expose the little lenses. There would be one here, 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 and so forth. John Grunsfeld, very active in all the way through the life of Hubble in installing instrument sets, the two of us together at a conference. And so COSTAR corrected, and you can click on these are active links. So it corrected the faint object camera, the spectrograph, and the high resolution spectrograph. Now subsequently, the COSTAR instrumentation was taken out And each of these instruments was replaced by astronauts with corrective optics built in. So COSTAR was in from 2003 to 2009 when they started pulling out the various instruments and the old ones and installing new instruments that had all the correction built in. And once again, here are those little tiny, very difficult to manufacture mirrors that popped up once this assembly was installed. Here's a picture of the version that sits at the Air and Space Museum in Washington, and there's the flight identification tag on that instrumentation. So here's the way Hubble is configured now. All the instruments have been replaced. COSTAR was taken out, and this is the area in which it sat. The wide field camera is now wide field camera 3. The fine guidance sensors have been replaced. And that was a limiting factor in the pointing control that John referred to, because the fine guidance sensors were looking at defective optics. So we now have a different suite of sensors in Hubble Telescope, a thing called STIS, the imaging spectrometer, cosmic origin spectrograph designed at the University of Colorado, advanced camera for surveys, and a new near-infrared camera and spectrometer that complements what the wide field camera can do because it operates in the infrared. Now, there are other things had to be fixed too. I can't go into all the details, but the original Hubble design was very inefficient even after COSTAR was installed, because the solar panels would vibrate every time they flew in and out of the shadow of Earth. And since the early days of 1993 or so, 3 sets of solar panels of different designs have been installed to increase the efficiency and get rid of the vibrations that the controllers had to wait for the telescope to stop shaking around every time they flew through the terminator, and that just wasted time. Now they're efficient, and they get a big fraction of each orbit is productive. In addition, the NICMOS instrument, this one down here, is no longer in service. It had a cryogenic cooling system that's consumed all of its coolant, and it's just sitting there idle, and we're not sure what they're going to do with that for the rest of the life. They also, in the early days, had problems with this door. This is the protective door, because they were concerned about the telescope accidentally pointing at the sun and destroying all the instruments. And so this was designed to close every time the Hubble went into a deep safe mode, which happened frequently because of vibrations associated with solar panels. And there's the number of times you can open and close this door is limited, where they did not want to get in a situation where the door was closed and they couldn't see the sky. Now, real quick, this is what phase retrieval does. This is where the genius of this work was done. Focus error was induced on purpose by moving the secondary mirror, and you see the image is way out of focus, and it gets better and better. It never gets better than a certain focus, and then it goes way out of focus again. And by analyzing these images and doing it with various mathematical techniques, Chris Burrows narrowed the problem down and figured out what was wrong with the telescope. Okay, that's the end of my presentation. John, I'm going to stop sharing.
Hold on, I'm having an issue here. Damn it, I can't see. Oh, there it is, share screen. Okay. Okay, folks, so why can't I, hang on, I'm an issue here, I can't, oh, there we go, all right. Yeah, so now we're going to show you fantastic images and discoveries. A couple we're going to talk about, or Ed will, like the first couple at the beginning, like the deep field. Most of these were going to just be ooh and ahs, and we'll go through in about 15 seconds or so. These images are all from NASA, so they're not copyrighted. So I'm You want to talk about this, Ed? I'm controlling it, and you've got a couple pop-ups, so let me know when you want the pop-up.
Okay, so this is pretty self-explanatory. We're looking back in time. So here's the present time. We're looking back toward the beginning of the universe almost 14 billion years ago. So from the ground, we can see back about 6 billion years.
So it's a little confusing. The formation of the universe is off to the right. So when
yes.
It's like 6 billion years, that's 6 billion years from the start, not from now. Go ahead, Ed. Sorry.
Oh, right. You're right, of course. So 6 billion years after the Big Bang. That's how far back ground telescopes can see. And they're really good now because they can correct for the atmosphere. But that's their kind of limit. Of course, they're looking through the atmosphere. There's an image called the Hubble Deep Field. If you haven't seen it, I urge you to look it up. And we're seeing galaxies at 1.5 billion years after. Okay, so John's going to show you a chart of that. Then Hubble Telescope was used to do what's called an ultra deep field. They just stare at the darkest spot on the sky, hoping to see something. And sure enough, after hundreds of hours of staring at the same place with exquisite pointing control, you can accumulate enough light to see the oldest galaxies, and their morphology is very different than the ones in this part of the universe, the more modern part. This has been done in the infrared, and the reason we can see farther back in the infrared is infrared works at longer wavelengths, and it's less influenced by dust along the vision path. And here's James Webb. This is going to be launched December 18th. A much bigger telescope that operates in the far infrared, and the expectation is they'll see back to just 200 million years after the start of the universe, when there were very few stars. There was a long period in the universe when it was total darkness until the first stars formed. There weren't a large concentration of stars until about 400 million years after the Big Bang. So James Webb is going to look way, way back looking for the first stars. Okay, John, you want to click on the overlays. Yeah, so we can't see farther back than this number. That's the first time the universe became transparent, and what we do see light there in the microwave, the so-called cosmic microwave background. All right, hit it again. And very important when you're talking to your friends and neighbors, Hubble and Webb do not operate at the same wavelength. So the press gets this wrong all the time. They say that the Webb telescope will replace Hubble. Not true. The Webb telescope sees wavelengths that Hubble cannot see, and the same is true. Hubble sees down in the ultraviolet, and Webb cannot see that. So their wavelengths overlap. Is there any? Yeah, December 18th. I think that's the end of the notes.
Yes, and here's the deep field. Do you want to talk about this?
Yeah, so if you look at the deep field, get the best version of this you can off the web, the highest, the largest file size, and then zoom in on it, and you'll see all sorts of odd-looking galaxies. You'll see occasionally something there, like that's a spiral galaxy that looks like the Milky Way, but in the deep field and the ultra deep field, you'll see galaxies that just aren't forming these days. These are the relics of the very, very early universe.
Can you explain the history of the deep field?
Oh, yeah. So this guy, Bob Williams, who I happened to go on a bike trip with, Bob Williams was the director of the Telescope Institute in the early 90s. And the Institute director gets to have some observing time, and he invested all his observing time in producing the first deep field image. And it was real simple. He told the controllers, point the telescope at the darkest spot on the sky and just collect light. And this is what you get. There's tons of stuff out there. Okay, keep going.
Want to comment on the ultra deep field?
Well, not really, except that this is a group of these. I mean, look at this thing. it looks like two galaxies sharing mass, but it's just so different than what we see in much more modern galaxies like the ones that we see from 3, 5, 10 billion years ago.
Okay. Now I'm going to go through a lot of these pretty quick. These are just some Hubble accomplishments, documenting death throes of stars, where stars supernova and die, and the birth of stars, where stars come in, like it is Carina Nebula, and I got a better image later. Finding planetary construction zones where planets are forming. Realizing monster black holes are everywhere. Looking at galaxies and the clusters of galaxies to try to figure out where dark matter is. And tracking evolution in the asteroid belt, Kuiper belt, discovering the Hubble was one of the telescopes used along with Mauna Kea and Kitt Peak, and discovering that the universe is actually expanding at an accelerating rate. Okay, so I'm not going to read through all of these. I'll put these up for a few seconds so you can go to the recording, the YouTube recording, and read it if you want. But this is shows a combined visible infrared light of Planetary Nebula. This is the Carina Nebula next. This nebula is in our galaxy. All these nebulas, these gaseous nebulas, are in our galaxy. It's a Carina Nebula. You can see some stars here, but here's the actual nebula. There's hydrogen spewing out, and this is also an area of stellar formation, second stellar formation, like our sun was, which has heavy materials in it, like calcium and iron and stuff that life needs to form. Okay, this is the Bubble Nebula, 7 light years across, a huge nebula. This is the Crab Nebula coming up. It's pretty close to us. There's a white dwarf in the center of this nebula that is about the size of about the mass of our sun, but it's the size, it's like just a few miles across. And this is the nebula caused by Tycho Brahe's supernova of 1054. So here's a new star being formed, and it's throwing out jets of stream. These are all Hubble images. So this is the Crab Nebula. I'm sorry, the Bell Nebula, which was an exploding supernova star, and it's just beautiful. And it's not only the beauty, the thing to look at, too bad John Wiltsey isn't on this, because he could talk about these boundary layers, is the incredible detail that it provides. And even with a synthetic star and phase conjugation, you really can't get this from our ground-based telescopes. So here's a galaxy that's a little bit smaller. It's smaller than the Milky Way, but it has a lot of interesting features. And this looks like it's IR, from the shortwave IR. These areas where it's blue are where stars are forming. And these areas where it's red are basically gas and nebula from supernovas. So these are where stars will form in the future. But here's where they are forming now. Okay, so this is kind of an odd picture. It's a trapezoid. It's a bunch of bright stars. And again, you can see the 4 spokes. And again, the Hubble wasn't really made to look at this. It was made to look at all of this, all of the low light and diffuse areas. So here's a galaxy coming in. And Ed, why don't you explain the gravitational lens on this?
Okay, so this is a result of a single distant galaxy producing light. All this light is from the same compact object, but in between, there's another galaxy. And actually, John showed a cartoon of the what's called Oh, yeah, scroll back.
Go back.
Well, never mind. We'll just leave it like it is. But the point is, this is close to being something that's frequently called an Einstein ring. If the intervening galaxy and the distant bright galaxy are on exactly a line connecting to our telescope, you would see a ring because of the way light is bent by that intervening mass, which could include dark matter, which is a mysterious thing. And the way we know that all this light's coming from the same place is if you put a spectroscopy probe on this, you see the same spectra you see here, everywhere. And all this light has the same Doppler shift, meaning it's receding from us at the same rate. So we can say all this light's coming from the same compact object that just happens to be nearly aligned with a bright object. That's what this is. And the light rays get bent. Just follow Einstein's equations and you see the light rays have to bend to travel as they travel past this intervening object.
So here's another galaxy in Hydra. And again, these blue forming areas are where stars are forming, and where it's kind of reddish or pinkish, that's where there's nebulas. And that's where there's gases. Okay, so this one's interesting. This is ARC 142. This is, if you look at it, it's a messed up galaxy. Doesn't look like spiral, doesn't look like a globular. It's interacting with another galaxy, and it's getting distorted. And NASA uses the word interacting, which is correct, because it's really not colliding. You can think of it as colliding, but one star may not ever collide with another star. It's just a gravitational interaction as these galaxies flow through each other.
And John, let me make a quick point about this. These areas that look like veins in a shrimp, those are dust lanes. Those are areas of high density of dust and gas, and probably are future. That's the locations of future star formation.
Right. Yeah. And this is our future. The Andromeda Galaxy is careening in, heading for us in Milky Way. It's much bigger, and it's going to distort our galaxy, and we'll probably distort it in a few billion years. Okay, now these are overlapping galaxies. These are not interacting. These are actually 10 million miles or 10 million light years from each other. So one galaxy, this spiral, we're looking on like top down, and this one kind of edge on, not quite, but they're not interacting. They're just overlapping. Like you've taken a picture of your spouse, and then there's a crowd 50 feet behind them. And here's the Ring Nebula, a beautiful nebula. There's a white dwarf. I believe it's that guy in the middle of it. Another galaxy from the Hubble. When you can see the incredible detail that you can see in this. And actually, the Hubble and infrared was kind of started cluing people that there's not enough stars in these galaxies for them to form together, and there's some dark matter. Now, this idea has been around since the 40s or 50s. Actually, Seifler and a few others, I think, at Mount Wilson started it. Here's an infrared image, I know from WIPIC 3 IR, of the center of our galaxy, looking in towards the center, which is normally occluded by gases and dust. Another beautiful nebula, gaseous nebula within our galaxy. Another beautiful galaxy out there. Another star cluster. Okay, so the Hubble didn't just do galaxies. It also did a lot of observations of our solar system. And here's an observation of a comet breaking up, where the comet's coming into the sun and actually breaks up into pieces from the Hubble. And here's Jupiter. You can see its moon Europa, Europa's shadow, Callisto, its shadow. And again, too bad John Wilsey's not on here to talk about these boundary levels that he gave a talk at a few months ago. These are so clear and these are so well defined, much more than you can get from the Earth. All of this interaction that has led to a lot of PhDs and a lot of papers and a lot of knowledge of how these gas giants, how these various gases are forming and working in their on their planet. And here's another one at Jupiter. Again, look at the amazing structure you can see in the boundary layers of these various gases. Here's the big red spot, which is actually decreasing in size. And Hubble and others have been monitoring that. And that's a shadow of its moon Ganymede. So if you were on the red spot below that shadow, you'd be in an eclipse. And of course, everybody's favorite, Saturn. And this is Saturn from the Hubble. These dark areas were discovered by an astronomer named Cassini. And Laura's going to talk about the spacecraft named after him in 2 months. And this is one of my favorite pictures of the Hubble of Saturn. This is Aurora Borealis on Saturn. That's its north pole. And this is a Hubble image of Aurora Borealis on another planet, on Saturn. Another amazing view of Saturn and its moons. Neptune, storms on Neptune, where, again, we see from the Hubble much more detail. It's more blurry because Neptune's further away, much further away than Jupiter or Saturn. Okay, finally, the Hubble was an amazing instrument. I don't like reading bullets, but I want to read this quote by Neil deGrasse Tyson. No matter what Hubble reveals, planets, dense star fields, colorful interstellar nebula, deadly black holes, graceful colliding galaxies, the large-scale structure of the universe, each image establishes your own private vista on the cosmos. It has served mankind for over 30 years. Well, hold on to your pants for discoveries of the James Webb. Over 6 times the light-gathering power of Hubble will explore X-ray events so redshifted they are in the infrared. It's 1 million miles from the Earth in the L2 Lagrange point. And I hope it works well. I hope NASA pulls this off, because it will peer into the formation of the universe, as Ed pointed out before. Like I said, it's like 6 times the size of Hubble. Here's an image of its primary. It's segmented and it's folded up in the Ariane spacecraft, the Ariane booster that will launch from South America. The prime contractors were TRW in LA, now Northrop Grumman. Ball Aerospace was a major subcontractor doing this. In fact, I wouldn't be surprised if this has images from Ball. Tinsley actually made these, and Teledyne, which some of you now work for, made the focal planes on this. So, with that, thanks to all over the decades that had the vision, logic, intelligence, ingenuity, and work ethics to make this machine possible for us. We all benefit from it. And if we have time, we can take some questions now. Unless, Ed, do you have some closing?
No, I'm eager for questions.
Can you close the screen sharing so we can have more room?
I'm sorry, say again, you broke up.
Close the screen sharing. End it.
Well, I was going to like this.
Up at the top, yeah.
So I have a question. In the deep space images, what are those are all false color images, right? Because you're not really seeing colors. And these pictures that you're showing, those are not, this is infrared or whatever.
Oh, no, wait. No, I'm sorry to interrupt. The ones in the visible spectrum are real color. The ones in the infrared are probably false color.
Well, they have to be false color.
They have to be false color.
Right.
Infrared. But no, I'm scrolling back to there.
So let me change the question.
So I can scroll back to what people
In the visible, do you really see these brilliant colors?
Yes, if you have a 2.4 meter telescope to look through.
I don't have one of those in my pocket.
Yeah.
In space.
Oh, okay, cool. Yep.
The picture you're showing now is my background, which happens to be the ultra deep field picture that I have loved. I have over 1,000 pictures taken by Hubble that, you know, I've been using. And I also give talks, but not to the depth you did. I learned so much and I really appreciate that. My favorite are nebulas, by the way, in terms of pictures. I think that it's amazing to look at. So this was great.
I have a question. This is first, if I can.
Sure, go ahead, Harold.
Yeah, this was phenomenal. I mean, I learned a huge amount. I have one thing that's confusing me a little bit about the Webb. I thought that recombination was about 380,000 years after the Big Bang. And so I'm confused about seeing before that, because I thought the universe was opaque to photons before that, but clearly
okay.
I'm wrong.
No, you're exactly right. We're looking at 380,000 years versus 400 million years.
Okay, thank you.
Yeah.
So we're still a long ways from the 380,000.
Well, no, we can see what has come to us from recombination when the universe became transparent, and it's called the cosmic microwave background.
Yeah.
But then there was a period of 400 million years of essentially total darkness.
Oh, so nothing there really.
Nothing. There were no stars, or the number of stars was so small that it was just insignificant in lighting up the universe. It wasn't until 400 million years when there was a big collection of stars distributed everywhere and galaxies started forming, and that turned on the lights.
Oh, so we're going to see then stars forming well before you got a distribution that really corresponded to the distribution of fluctuations in density, because you're seeing only a few lighting up. Wow.
Yeah, exactly.
Wow.
We have a question from someone. It says, how does James Webb's orbit compare to Hubble?
Oh boy, it's not an orbit. It's at the L2 point, 1,000,000 miles from Earth.
It's an orbit around the sun, essentially.
Yeah.
Oh, okay.
Yeah, it doesn't orbit the Earth.
Got it. I'll bring up a picture of that while you guys are talking about other things. So just to make it clear, Hubble is in orbit around Earth. The L2 point, I have a picture here. Let me share my screen briefly. John, can you drop up?
All yours. Yeah, it's about 1,000,000 miles from the Earth, and there's other telescopes in it right now orbiting this. It's an unstable Lagrange point. Every 23 days, they need to correct it, but it has a lot of advantages for observing where the Earth, with the Hubble, every 45 minutes, the Earth gets into.
Yeah, I'm simulating that right now, John. I'm just moving my cursor around Earth. Right. Every 90 minutes it goes around, but it flies in and out of the terminator.
Right.
Here's Earth, what's called Earth-Sun L2. So this point moves around, takes a year to go around. The other reason they're out there is it's really cold. The telescope is the Hubble, the Webb can only function if everything on board except the spacecraft electronics is cold. And so they get away from radiant heating from both the sun and Earth. And so it's out there, it's got huge radiators to make it as cold as possible. It'll take many months for Webb to cool down. So they're going to launch in December. It'll probably be March before they actually have the telescope cold enough to actually start doing imaging. But it just moves along as Earth moves around the sun, the L2 point follows along. I hope that answered the question.
Yeah, that is great. So, of course, this begs the question: it would be great to have a talk sometime about the Webb.
Yeah, well,
what they expect to do with it.
Yeah, and John and I have talked about we have enough material to talk for days about the goals of the Webb telescope.
Good.
Yeah, but let's wait until it's launched, and I hope it works. I mean, It's a pretty daring mission. It's spending a $10 billion telescope 1 million miles from the Earth, and it deploys the mirror. The mirror actually unfolds.
Yeah, it's not serviceable.
Well, and it's not serviceable. And I say NASA screwed up. Ed and I disagree with that. If you can put it there, you could put a robot to service it 5 years from now or 10 years. But it's not designed to be serviceable. So it's not serviceable.
Yeah, so once again, here's the sun, Earth, and there's an array of Lagrange points. These are gravitational balance points that have been known about since the 1780s, but we're exploiting this one. And actually the Webb will have a very slow orbit around L2 as L2 progresses around the sun.
Yeah, so Ed is right. It's completely unserviceable by the way it's designed. Whereas the Hubble, everyone thinks it's not serviceable anymore, but we got that docking mechanism there, and we got vehicles that can now go to its orbit. So who knows? Who knows what NASA, there is a possibility of a service mission to the Hubble again.
Necessity is the mother of invention.
Yeah. It looks like Harold's got a question.
Just a small statement on Lagrange points. You just understand the L2. You could just understand that you're in an orbit farther from the sun than the Earth. So you'd be going around slower, but you're feeling the Earth's gravity as well as the sun's gravity. You're right in that line. So you have stronger gravitational force, and that's what's giving you the balance. And the same for the one that's inside, this one where it would be going faster, but the Earth is pulling it away from the sun.
Right. Yeah, there are actually 5 Lagrange points.
Yeah.
Okay, other questions?
Well, thank you. And I got to send a shout out to Neil Bertram. I think he's up the latest to watch this. He lives in the UK.
Yeah,
I have a question about the Lagrange points. Aren't some of them unstable?
Yes.
Yes, including this one.
Yeah, this is not stable. They have to invest a little bit of energy using electrically powered thrusters to stay, as I said, they're going to have to stay in orbit around this point. So actually,
I think they have hydrazine, not ion thrusters.
yeah, and it's okay. I mean, they're not going to contaminate their...
Well, I disagree, but anyway, go ahead.
They can, well, here's the way to say it. They can tolerate a monolayers of the small amount of material that gets on the mirrors will not affect the science output. That was obviously the first thing they thought about, is how do we make sure if we use thrusters that we're not going to adversely affect the science.
Yeah, and back to the Hubble does not have thrusters. It has reaction wheels to control it. Which,
right. So here once again, here's am I sharing my screen?
no, sure.
Okay, take me a second. Bear with us, ladies and gentlemen. Okay. So this is a better picture I found. So here's Sun, here's Earth. This is the Moon's orbit. And then very close to Earth is the Hubble orbit going around like that. And here's the Webb orbiting around the L2 point. And you see here some detail. It takes 6 months roughly for the Webb to go around this little tiny depression illustrated here in the gravitational field that results from the Sun, Earth, a little bit of influence from Jupiter, and so forth. It's a more complicated problem than just the Sun and Earth. Now, at the same time, Earth and the Moon have a set of Lagrange points, but that's not pertinent to our conversation right now.
Actually, the Webb won't be the first telescope there. There's
No.
other space telescopes. The YMAP and Planck are both there, and I think a couple others.
Yeah. It's a good place to be if you have to be cold.
As infrared sensors like to.
Yeah. So listen, everybody, if you have additional questions, both John and I can be reached through Bruce, or you may have our emails already. If you're interested, you can send us questions and we'll answer them through email.
Thank you. This was very, very informative, very interesting.
Great. Good to hear that.
And I've learned, and that's what's good, because I know enough, but didn't know the details like this.
Yeah.
I was there. I remember that first image on television, how disappointed I felt. It was blurry, you build this up and then it was gone.
Well, if you're interested, this is the book you might want to get. You can probably buy a used version for $5.
Okay.
Now, I know this was written by Eric Chasen, who was the chief public affairs officer for the Telescope Institute when Hubble was launched.
Right.
Now, I know many of the people that are in this book, and a few of them have said there are errors in the book. But on the whole, this is the best resource you can find if you want to know the details, and there's tons of drama in here. This is like reading about the housewives of Los Angeles or something. All the people threatening to kill other people, the bad behavior of the characters who were involved in the drama at the beginning is astounding. But I'll give you one quick example, since Bruce hasn't told us we got to stop. Before Hubble was launched, people had submitted proposals to observe particular galaxies or nebulas or something. And when Hubble was found to be defective, the press office, headed by Eric Chasen, who wrote the book, said, we've got to give some pictures to Congress and the public. Months had gone by with no pictures, and we spent billions of dollars to build this observatory, and Congress is losing their minds. And the science community and the public want to see images too. We've got to pick an image that doesn't look terrible and provide it. So they spread the best pictures they had out on the table. And they invited lead scientific people who were intending to do research with Hubble. And they invited them into the room and said, which of these pictures can we release to the public? And that's when these threats came up. And this is a quote, I actually know who the person is who said this. If you release that picture, I will kill you. because it was a picture that person had proposed, a region of the sky they had proposed to study in detail, and they had grant money and they were ready to go, except Hubble was not producing images worthy of doing any science. So there were all this contention and anguish before they finally released. After about 3 months, they started releasing pictures, and the public did not know that the pictures were as bad as they were, because the public in general is not looking at the best pictures you can get from the ground. The idea was to do, 10 or 50 times better than you can do from the ground. And the public in general is not looking at pictures taken by ground-based telescopes. They're marginally interested.
I got a little story that
yeah, go ahead.
Tell about this. So when that was going on and the images were terrible, I was bitching, I believe it was to Bill Bloomquist, who some of us know. And I said, I can't believe Lockheed screwed up so bad in Perkinoma that they didn't do a full test of this. They should have done a full test. And I believe it was Bill Bloomquist. He looked at me and said, I'm glad they didn't do a test. If they did a full test and found the spherical aberration, Congress was so mad at NASA for overspending and being behind, it would never have been launched.
Right.
And we never have had it. It was a good thing they did do the test.
Yeah. And it took 3 years to recover.
Yeah.
Well, I know from the work, the places that at FLIR, I don't know how many times we would start a project and the engineers would go, well, let's get started on this thing. We don't really know what's going to cost, but we're going to have to tell them what they want to hear. Otherwise, no science would ever be done if anybody knew how much it would cost. But what you get out of it is so worthy that you have to somehow use a little bit of subterfuge to get started.
Yeah, you have to try to do great things. Now, the Webb telescope, assuming it deploys properly, does have more control because, as John pointed out, it's a segmented telescope. They can change the shape of the primary, not a lot, but they can change it some. Hubble's telescope primary could not be changed in shape. And so Webb has a little breathing room, and it has to, because the structure is so physically large that over time, the metering pieces that are made out of synthetic materials like carbon fiber materials, those pieces are going to change size because they're going to leach out material and a little tiny bit of residual water vapor. So they got to be able to correct for those slowly changing things. And maybe once a year, they'll have to correct the shape and position of the optics.
Yep.
Now, the flip side of what you said about the images is when I teach astronomy, I have to remind students that our 5 to 12-inch telescopes are nowhere near the Hubble or even other the high-end ground-based telescopes. So don't be disappointed when you look at what we see from here compared to what you're seeing. And I've got extremely dark skies near me. I'm fortunate on that. I mean, really, really dark.
Yeah, I mean, you compare the average astronomer maybe has a 4 or 5 inch telescope, and the Keck, the biggest telescope we have, is 2 of them on Mauna Kea in Hawaii, 10 meters in diameter.
Yeah.
So, but outer space is the place if you want to take good pictures without stray light, scattered light, absorption by the atmosphere. And if you want to be productive, I mean, ground-based telescopes can only function at night.
And LEO satellites.
What's that?
And low Earth orbit satellites.
Yeah. Yeah.
There's thousands of them. Well, I think we should probably wrap this up, Bruce.
Yeah, we have some really good stuff coming up, guys. And I also found another speaker that we may employ that is a chemist, Mr. Cunningham, one of your fellow chemists. You'll have an ally here. Too many physicists in this group for chemists.
I know.
But let's put your cameras on. How many thumbs up do we have here? for this.
I'm
giving
yeah.
two here.
Me too. John,
Yeah.
if John had his video, he'd be voting that we did a good job.
Yeah, beautiful job, guys.
All right,
Thank you very
thanks.
much.
It was fun to put together.
See you next month.
Yeah, great.
Who's next month?
Yeah, who's
It's
talking?
Laura Dafoe, the introducer tonight.
Oh, no, she's December. I
Oh.
thought Corinne was next month again.
Oh, Corinne is next month. Corinne Foster. Yep.
Great. It'll be good.
We're gonna go back to anthropology.
Beautiful. Okay. Good night, everybody.
Bye-bye.
Bye.